All right, so the plan for today is just to finish up, whoops, I have these in the wrong order. Finish up Bayes' theorem and start chapter 6 on continuous probability distribution. So that's the plan for today. And the quote of the day for today is from a friend of mine, Mark. I knew him in St. Louis. He's in finance, and he said this one time, and I wrote it down because I thought it was such a good idea and such a quotable quote that 10 times out of 10 I would take a questionable contract with a solid person over an ironclad contract with a questionable person, right? And I think of this a lot when I'm, say, hiring contractors or something like that. When I need somebody to work on our house, I'm much more comfortable with the person who I would take a handshake from, even if the contract is a little questionable or if they don't really, do the whole formal contract thing. I'm much more comfortable working with that person than the person who, seems pretty shady, but the contract's ironclad, right? I mean, if you have to take somebody to court, you've already lost. So, uh, yeah, I thought this was an interesting quote. It kind of related to our quote from last time, the Marcus Aurelius, stop arguing about what it means to be a good man, be one, right? So, and also this is a reminder to me that, I would like to be the kind of person who somebody would take a handshake from and wouldn't demand a formal contract or, you know, now that's not to say it's good to have formal contracts to lay out expectations and all of that, but the point is that, you're doing the deal with the person, not with the piece of paper. Okay, so continuing on with Bayes' theorem, we started this problem last time, and the setup was this is kind of a Bayesian machine learning example. The setup was we're an auto insurance company, and we are trying to set premiums for our insureds. So we have three types of drivers. We know that if we were omniscient, if we knew everything about the world, we could look at a certain driver and know that they were either a good driver, a moderate driver, or a bad driver. And we know that in the population of insureds that we have, 30% of them are good drivers, 50% moderate, 20% bad. And because bad drivers tend to cost us more money, they tend to take more money out of the pooled resources. We charge them more money for their premium, so they have to contribute more in to the pool to balance that out. And just the opposite for the good drivers. They tend to take less money out of the pooled resources. They have to contribute less to balance that. And the moderate drivers have to take, and they take a moderate amount out, have to contribute a moderate amount. We also said we know a bit about the behavior of each type of driver. If we knew that somebody was a good driver, they would get in 0 accidents per year, 65% of years, 1 accident per year, 35% of years, and 2 or more accidents per year, never. A moderate will be 45, 45, 10, and a bad driver will be 30, 40, 30. So the first question we asked was, what premium should we charge a new driver if we have no information about them? And what we came up with was basically using the expected value of this distribution. Or basically, instead of saying, if I have 100 new drivers that come in and ask for insurance, I can't pick out which ones are the good, which ones are the moderate, which ones are the bad, but I expect that there will be about 30 good drivers, 50 moderate, and 20 bad drivers, but I don't know which ones are which because I have no experience with them and I'm not omniscient. So what I do is I kind of treat each individual driver as like a mixture of good, moderate, or bad. I say this person, driver one, is like 30% of a good driver, 50% of a moderate driver, and 20% of a bad driver. And that's my argument for using this weighted average. So that across all those 100 people, the people who are truly good drivers will be paying a little more than they should, and the people who are truly bad drivers will be paying a little less than they should. But overall, those 100 folks will be contributing into the pool as much as they are taking out of the pool, and things will be balanced. I don't want to charge over that. I don't want to just charge everybody the bad driver price because then my competitor can come in and undercut me. I don't want to charge under that. Just say, we'll charge you all the good driver price until we see that you get into wrecks. Well, because then we're going to draw the pool down and our insureds who are paying into the pool and expecting to be covered, at some point we're going to have to turn around to them when they go to make a claim and say, oh, sorry, we don't have any money to pay you, and go bankrupt. So that's not good for anybody. And I made a little Excel sheet over here where we just have our priors, our probabilities, our premiums for each of those, and then our end premium for this individual. So for the person we have no information about them, we would charge them $135 a month to start. But then the thing is that as we have more and more experience with them, as they're with us for a year or 2 or 3 years, we start to get more information about what kind of driver they are. Each year they might get in 0 accidents or 1 accident or 2 or more, and we can take that information and see whether that lines up more nicely with them being a good, moderate, or bad driver, and maybe start to adjust our estimate of what type of driver they are. Maybe if they got in no accidents at all for 3 years in a row, their probability of being a good driver would go up quite a bit, maybe to 0.6 or 0.7. Probability of being a bad driver would go down a lot, maybe to 0.05, and moderate filling in the difference. And they would be paying much closer to $75 per month instead of $135. On the other hand, if they got in a bunch of crashes, it might go the other direction. So intuitively, we understand that that's how it should work. How do we carry that out? Well, we took an example here. Let's suppose that in their first year of experience with us, they got in 1 accident. So our priors for year 1, if we think of the timeline, so here's like year 1, this is time 0 when they first started with us, and this is time 1 year later. The priors for year 1 is kind of our estimate for the good, moderate, or bad driver likelihood for this person at time 0, at the beginning of year 1, prior to our experience in year 1. During year 1, they got in 1 accident. And then what we want to get is posteriors for year 1. In other words, at the end of year 1, what is our revised likelihood of them being good, moderate, or bad driver, based on not just the 1 accident and not just the priors, but a combination of those two. Our kind of overall worldview, our overall previous guess at the likelihood they were a good, moderate, or bad driver, and this new piece of information, they got in 1 accident. And we went through that systematically last time. I won't go through the details again, but these were the details. And we ended up with about a 25.6% chance they were a good driver, about a 54.9% chance they were a bad or a moderate driver, and about a 19.5% chance they were a bad driver. And we can take the weighted average the same way that we did up here. We're using the same numbers, 75, 125, and 250. Maybe in reality, we would adjust these numbers each year, as well as our costs and expenses and predictions for claims and so on, change year over year. Things get more expensive to repair and so on. But for this problem, we're not taking that into account. So our new premium for year 2 should be $136.58 or so. So the premium didn't change very much for getting in 1 accident in the first year. And we saw that our probability of being a good driver went from 30% down to about 25%. Moderate went from about 50 to 55, and bad stayed about the same. So we just put a little more weight in moderate, a little less weight in good driver, but not a huge change. Getting in, 1 accident a year is maybe kind of what we expect overall from our population. Now let's look at the second year. So we had year 1. This was time 0 and time 1. They got in one accident in year 1. And then let's look at year 2, going from time 1 to time 2. Remember, our premium was 135 at the beginning of year 1. That's what they paid for all of year 1. And then it's 136.58 for all of year 2. And let's suppose that in year 2, they got in 2 accidents. So that was kind of a bad year. Got in 2 accidents in year 2. Now let's do the same process. Let's update their probability of being a good, moderate, or bad driver in light of these 2 accidents. Now note that kind of at the very end of year 1, we had a posterior for year 1 after including this 1 accident piece of information. That posterior for year 1 is at time t equals 1, just at the end of year 1. This is our guess, our estimate for the probability they're a good, moderate, or bad driver. 25, 55, and 20% or so. But note that that posterior for year 1 is really just the prior for year 2 as well. Right, that's our estimated kind of time t equals 1 at the very end of year 1, but that's also at the very beginning of year 2. So when we're creating their premium for year 2, that posterior for year 1, we take that to be the prior for year 2, we create our premium, and then we push forward with that. And now I want a posterior for year 2. That's my next goal. What feeds into that is the prior for year 2, my kind of initial suspicion that they were a good, moderate, or bad driver, as well as my new piece of evidence that they got in 2 accidents this year. I don't want to like re-include the 1 accident the previous year. That's already taken into account in the posterior for year 1 or the prior for year 2. So that's already taken into account here. So I don't need to like re-include that piece of information. That's already accounted for. But the new piece of information is the 2 accidents in year 2. So let me copy these down. So my posteriors for year 1, well, again, we're just thinking of these as the priors for year 2. So this kind of just becomes probability of good, probability of moderate, and probability of bad unconditional when I'm thinking relative to year 2. And now I would just want to do the same thing that I did before, but now with year 2 with 2 accidents. So I'm kind of like bootstrapping my way along here. I'm using the evidence from year 1 to adjust my probabilities, then kind of wrapping that up, sealing that up, and then looking forward to year 2, looking at the evidence for year 2. In this case, they got in 2 accidents. So my question now is, what is the probability of them being a good driver given they got in 2 accidents the second year? Well, again, from Bayes, there are, well, this is probability of 2 given good times probability of good over probability of 2. So all the ways they could get in 2 accidents, but there are 3 ways they could get in 2 accidents. They could be a good driver and get in 2 accidents, at least in theory. Or they could be a moderate driver and get in 2 accidents. Or they could be a bad driver and get in 2 accidents. Well, these probabilities, the ones that are unconditional, are related to our prior for year 2. So I can write those in. Again, I won't write in all the percentages, the percent signs, because I'm going to have a percent squared in every term in the numerator and denominator. They're just going to divide out. So 25.6 on the top, as well as in the first term in the denominator. Probability of moderate was 54.9%. And then bad 19.5. And now I need to know my conditional probabilities. Probability of getting into accidents given the person's a good driver. Same for moderate and bad. And here we refer back up to our little chart up here. Given they're a good driver, what's the probability they get in 2 or more accidents? Actually 0 according to our model. And then 10 and 30 for the moderate and bad. So this is 0, 10, and 30. Let's bring up our calculator and do this really well. This one we actually don't need to do, but the next one we need to do. This one is clearly 0. 0 times something in the numerator gives me 0 in the numerator. The denominator is clearly not 0, so this is just 0. So based on this 1 year of 2 accidents, probability that they are a good driver has gone down to 0. Essentially because what our table says is good drivers absolutely never get in 2 or more accidents. It's impossible for a good driver to get in 2 or more accidents. So of course, if we look at somebody and they got into 2 or more accidents, they cannot be a good driver logically. That's not fuzzy logic or statistical logic. That's just mathematical propositional logic. Good drivers cannot get in 2 or more accidents. Somebody got in 2 or more accidents, they cannot be a good driver. Now, what about moderate? I'm going to use red for this because that's the only color I have left. Probability of moderate given 2 is probability of 2 given moderate times probability of moderate over that same denominator. The probability of getting in 2 accidents, that denominator stays the same. We're just now asking what is the relative size of this middle term to that whole denominator. Before we were asking what's the relative size of the first term to the whole denominator. So now I just have 10 times 54.9 over that denominator. So let's do that. I have 10 times 54.9 over, and I better put in parentheses here. I have the same thing. 10 times 54.9 for my first term. This very first term of the denominator is 0 times something, so it goes away. Right, that zeroes out. So my first non-zero term is 10 times 54.9, and then plus 30. Oh, wrong window selected there. 10 times 54.9 plus 30 times 19.5. Let me check that. Looks good. And that's about 0.484 or so. So probability of being a moderate driver, given they got into accidents, about 48.4%. So our moderate driver likelihood is still hovering more or less around 50-ish%. But what's the probability of being a bad driver now they got into accidents? What's going to be 100% minus 48.4% minus 0%? I'll keep being on the wrong window here. 1 minus our answer. If I do second negative sign, that pops in my previous answer. That's about 51.6%, which I could have done in my head. Don't know why I used the calculator for that, but so now these are my posteriors for year 2. Right. So that's at this point, after the experience from year 1 and the experience from year 2, the 1 accident and the 2 accidents, looking forward, now my estimate for this person is that there's a 0% chance they're a good driver, 48.4% they're moderate, 51.6% they're a bad driver. How does that affect their premium in year 3 when I reevaluate their premium at the end of year 2, beginning of year 3, and send them a bill and say, this is what you need to pay us if you want to remain insured with us? Well, let's see. Good went to 0, moderate went to 0.484, and bad 0.516. Their premium has gone up pretty significantly, 189.5. Right, so their premium went from 135 up a little bit to 136.5 or so, but not by much. That 1 accident was maybe something like about what we'd expect from our population overall. But then the 2 or more accidents really bumped their premium up quite a bit. Now, interesting little side question. Let's suppose that they got in 0 accidents the next year, or even 0 accidents the next 10 years in a row. Can their premium ever get down really close to the good driver premium of $75? So what's like probability of good given 0 now for future years? These posteriors for year 2 are like priors for year 3. So probability of good given 0 is probability of 0 given good times probability of good driver over probability of getting in 0 accidents. But now this is going to be 0. So what happened? The 0 from this conditional probability, this 0, cascaded over here. But then that is going to cascade for the rest of this person's, time with this insurance company. They could have 10 perfect driving years in a row. They're probably to be a good driver is still going to be 0 under this model. In a sense, that's kind of sensible because our model made the claim that it is impossible for a good driver to ever get in 2 or more accidents. And this person has at some point gotten in 2 or more accidents in a year. So logically, that makes sense, but practically maybe not so much, right? As an insurance company, maybe we would want to put like 1% here. If we put 1% here, right, that's going to really penalize the person for getting in 2 or more accidents. It's going to shift these numbers to maybe something like 2% and 49% and 49% or something like that. So they're going to be paying basically the same premium. But then if they have like 10 good years in a row, they can like still dig themselves out of that, right? So that's why we always want to be cautious about including things like 0% or 100% impossibilities or certainties in models like this. It can have some unexpected consequences. So the fact that this number here is actually a 0 instead of like maybe 1%, that has the consequence that if anybody ever gets in 2 accidents in a year, they can never be considered a good driver again. So their premium could never go below $125. And if that person has 10 years in a row with no accidents, I mean, there's probably going to be quite a few insurance companies happy to take them on for the good driver premium, and we're going to lose that business. We're going to lose the business of the good drivers. That's probably not what we want. Any questions on this example? And I guess this is example 4. Okay. And as a side note, I mean, you can kind of see that this is just algorithmically tracking basically what's your performance and turning that into a premium. This system is essentially learning what kind of a driver you are, whether you kind of mesh with this, that, or that description better. It's essentially learning that through experience and just using Bayes' theorem to incorporate new information. I have some simulations that I'll post on Blackboard in the supplemental material folder. Um, if you're interested in coding and that kind of thing, you might find these interesting, but even just this simple model does a pretty decent job of separating if you have actual good, moderate, and bad drivers, and you kind of behind the scenes assume that you know which one is which. The question is like, does this actually separate the three groups pretty well? Do the good drivers after a period of time end up paying close to $75, the moderates close to 125, and the bads close to 250? And the answer is yeah, it kind of separates the three groups pretty well. It's probably not the best or the most efficient way to do it. And of course, in the real world, there are lots more variables and there are lots more things that change. These numbers are going to change every year. Um, Things like, once you hit a certain age, if you're, 18 or 20 or something, you're probably going to be paying higher rates just because of that. Once you hit 25, your rate's probably going to go down. It might be dependent on the type of car you drive, or of course, the type of insurance that you choose. Do you want comprehensive or collision? All of that. So there's a lot more that go into this. But I think as a demonstration, this kind of shows how this type of model could work. And there are things like loss leaders. Like maybe our company, maybe we do actually choose to charge new drivers the good driver premium, $75, knowing that we're going to, lose a lot of money that first year, or maybe 2 of experience with that driver. But maybe we think that while getting them in the door, getting them signed up for a policy, they're probably just going to set it on auto pay and forget about it. And, we can hike the rate a couple years from now and make our money on the back end, right? So they can think of it as a loss leader. There's all kinds of other components that go into this, but I think at a surface level, this gives an idea of how a model like this might work. Okay, and then one last example. Going back to a medical testing example, and one that's a bit more straightforward. So we've gone through a couple that were not so straightforward here to hopefully show you how this can be used in more realistic real-world scenarios. But here's an example that's a little bit more straightforward. So pregnancy tests often claim to be, quote, 99% accurate. It's not it's not very clear what that means, but let's assume that means that sensitivity and specificity are both 99%. In other words, the true positive rate and the true negative rate are 99%. So if you're pregnant, the probability it says you're pregnant is 99%. And if you're not pregnant, the probability it says you're not pregnant is 99%. That's what we're assuming here. Now let's look at 2 scenarios. Suppose that one woman is trying to not get pregnant, making a concerted effort to not get pregnant. And at a given point in time, she estimates there's a 2% chance she's pregnant. She takes the pregnancy test, comes up positive. What's the posterior probability she's pregnant? In other words, what's the probability that she's pregnant given the positive test? Her prior estimate of being pregnant was 2%. She now has new information that the test came back positive. We know the tests aren't perfect, right? It's only 99% accurate. So should she just assume that she's pregnant now, or should she, look to do some kind of follow-up testing? And then let's look at another scenario. Suppose a woman is trying to get pregnant, and she estimates there's a 25% chance she's pregnant. If she takes the test and it comes up positive, what's her posterior probability of being pregnant? And then looking at which test is more informative, which test is more, in which case is the test more useful, why is that? Okay, so let's look at part A. So her prior probability of, I don't really want to call it disease, that sounds kind of bad. Let's say probability, I'll just write it out. I also don't want to write like P parentheses P because we already use the letter P way too often in stats. So probability of pregnant is 2%. So probability of not pregnant is 98%. So these are our priors. This is the estimate, you know, whatever it may be, for whatever reason, she comes up with this estimate, but it's not based on anything to do with the pregnancy test. Then she takes the pregnancy test, it comes back positive. We want to incorporate that new piece of information in with our prior distribution, with our previous worldview, combine the two together to update our worldview, to update our belief that she's pregnant versus not pregnant. So what's the probability that she's pregnant given the test is positive? Given that the pregnancy test indicates that she's pregnant. Well, this is probability the test is positive given pregnant times the probability she's pregnant over the probability the test is positive. But the test can be positive in two ways. It could be a true positive or a false positive. My numerator stays the same. But then it could be a true positive. It could be that the test could be positive and she's pregnant. That would break up like probability of positive given pregnant times probability of pregnant. Or mutually exclusive, it could be a false positive. The test could be positive and she could be not pregnant. So that's probability of positive given not pregnant times probability of not pregnant. So these three come from our priors. So probability of pregnant, 2%. Again, each of these factors in the numerator and denominator is going to have percent squared. So, or each of the factors is going to have percent, each of the terms is going to have percent squared. So I'm just going to divide out all the percents. Make things easier to write. And then we have our conditionals. Okay, so let's take a look at sensitivity and specificity are 99%, and let's say what that means in terms of probabilities. So the sensitivity is the true positive rate. It's the probability the test is positive given pregnant, and that is 99%. And the specificity is the true negative rate. It's the probability the test is negative given not pregnant, and that's also, this keeps popping up. I have to figure out what is going on with Office. I swear, ever since they switched Office to 365, it's like nothing but little minor annoying mosquito bite type problems. But there we go, 99%. So sorry if that window popped up. And so the specificity probability of negative given not pregnant is also 99%. We need probability of positive given pregnant. That's the sensitivity. We need probability of positive given not pregnant. That's 1 minus the specificity. So I don't want to write it in green, maybe I'll write it in red. So probability of positive given not pregnant. These are complementary events. Given that somebody is not pregnant, the test either comes back positive or negative. We're assuming the test number comes back indeterminate, that we can't really tell the difference. So that's 100% minus 99% or 1%. So it's just 1 minus the specificity, 1 minus the probability of negative given not pregnant. So probability of positive given not pregnant is 1%. That's here. And probability of positive given pregnant is 99%. That is here and here. Okay, and we can come over to our calculator now. We need to do 99 times 2 over, and we need parentheses, 99 times 2. There's my numerator showing up as one of the terms in the denominator, plus 1 times 98. And that's about 67%. So the prior probability of pregnant of 2% with the positive test result became a posterior probability of about 67%. That's definitely a huge increase, maybe 30 to 35 times as likely. But if I told you that, something was true with probability 2/3, you wouldn't be very confident in that, right? If I told you that, whatever you type into this calculator, it gives you the right answer 2/3 of the time and the wrong answer 1/3 of the time, you would probably throw that calculator out and get a better calculator, right? So right now she says, she's much more concerned that she's pregnant than she was initially, but it's certainly not conclusive, right? You probably want to go follow up, get a more detailed test with a doctor. Now, what about part B? So for the woman who's trying to get pregnant and estimates there's a 25% chance she's pregnant, and then a 75% chance she's not pregnant. Well, what has changed? Well, actually, all of these conditional probabilities stay the same. They have something to do with the test, not with the person taking the test. These conditionals are the sensitivity and specificity, are aspects, the characteristics of the test itself. The green ones, the priors, the probability of pregnant, probability of not pregnant, those are what incorporate the information from the individual. So that's where her kind of previous worldview comes into play. Whatever made her think that it's 25% likely she's pregnant. So this changes to 25, this changes to 25, and this changes to 75. But the 99s and the 1s stay the same. Those are characteristics of the test itself. They don't change from person to person taking the test. So what do I need to do? 99 times 25 over 99 times 25 plus 1 times 75. That looks right. And here I see about a 97% chance. So for person B, their initial estimate was 25% chance. They took exactly the same test with the same sensitivity and specificity, and it came back positive. But their updated probability of being pregnant is 97%. So we went up by only maybe 4-ish times as much, right? The blue one went up by 30 times, this one by 4 times. So the blue one kind of changed the worldview in some sense more, but it changed the worldview from a point of fairly certain that she's not pregnant to kind of inconclusive, might or might not be. The red example changed from fairly inconclusive, might or might not be 25% versus 75% chance, to pretty conclusive that she is. Right. So doctors like to run tests like this, where there's a relatively high index of suspicion, a relatively high estimate in their opinion that you have the disease or that whatever they're looking for. Because these tests, okay, if it comes back positive, then I'm nearly certain and I can treat you. We can actually do something as a result of this test. It's informative, it's helpful, it changes treatment. Doctors tend to not like these tests as much, with quite a few caveats, right? I'm speaking very broad strokes here. Because especially if you imagine a situation where all that you can do is this test and there are no other tests you can do. Now, of course, with pregnancy, there's lots of other tests you can do, ultrasounds and all that kind of stuff. But if it was a different situation where this is kind of the only test out there for this disease and we have a low index of suspicion, we think it's unlikely you have the disease, but then the test comes back positive. It's like, well, now what do we do, right? Like the patient is probably going to want to be treated because the test was positive, but might uh, you still might not be very confident they have the disease, or you might even still lean towards them not having the disease in a different situation. But the patient wants to be treated because the test is positive, but the doctor doesn't feel that the treatment is warranted even now. It makes the decision-making process very difficult and very complicated because what does it mean if we say that like the probability is 50% or something that you have the disease? Should we treat? Should we not treat? Um, but something like this is much more clear. It's like, okay, we'll, start you on OB appointments and vitamins and all that good stuff and um and presume that she's pregnant in this case. So, okay. So which one is better or which one is more useful or which one is more informative? It kind of depends on your perspective. In the specific perspective here, like going from thinking you're not pregnant to thinking that you might or might not be is probably going to lead you to follow up with a doctor, maybe start taking vitamins or something, those kind of things, just in case. Um, and it changed our thought process by a factor of 30, but it changed it from, pretty certain not pregnant to not really sure. So it kind of cuts both directions, right? This went from not sure to pretty certain we are pregnant, but it only changed it by a factor of 4, right? Most people like these kind of tests and not so much these kind of tests, but as far as what's more informative or useful or whatever, it's going to depend on context, and it's going to depend on things like uh, how risky is the treatment. Just taking some vitamins and going in for an ultrasound isn't risky at all. And it's going to depend on things like, is there another follow-up test that we can chain another 1 or 2 steps on here? Can we say, okay, after the ultrasound, which is this and that percent sensitive or specific, now we have a prior of 67% going into the ultrasound. If we see something or don't see something, right now we can keep on chaining more pieces of evidence on. So, uh, so anyway, I would say it's context dependent probably, but probably, at a very surface level, the red example is more informative because as a result of the test, we get near certainty she is pregnant versus as a result of the test being kind of inconclusive, uncertain whether or not she is. All right, so that is Bayes. So we went through, I think, 4 examples with Bayes' theorem. And as I mentioned before, there are additional examples on a supplement in a supplement on Blackboard on the supplemental material folder. So take a look at that if you want to work through a few more examples. This is actually one of those problems on there. But there are a couple others as well. All right, let me switch my screen share back for chapter 6. Get things recombobulated here. All right. Okay, so we're shifting gears again. We were talking about Bayesian statistics, and remember that's where I mentioned that there's this different way of thinking about how to apply the mathematical model probability to the real world and kind of what that means, right? When I say that whatever, there's a 67 or 97% chance this woman's pregnant, what does that mean? I don't get to, or this woman doesn't get to like carbon copy herself 100 times and run 100 similar experiments and, come out actually pregnant 97 and not pregnant 3. This represents something more like a degree of belief, right? What life choices is she going to make uh, on the basis of this number? We're shifting gears kind of uh, not so much in chapter 6, but in basically from this point forward in the course, we're shifting gears back into the frequentist mindset, where when we start applying these probability distributions, especially in chapters 7 and 8, we're imagining that idea more like rolling a die, right? Where I can have 100 or 1,000 carbon copies of the same experiment and kind of average over them. And that's what my probabilities and expected values and so on really are representing. Okay, so shifting gears back to frequentist statistics, where we'll essentially be for the rest of the course. We're moving into continuous probability distributions. And before we do that, I want to remind ourselves of some ideas related to discrete probability distributions. Remember, we describe a discrete probability distribution by enumerating it in a table like this, typically anyway. Some of them are infinitely long, like the Poisson distribution or geometric distribution. But we imagine that if I have a certain outcome, I can ask, what is the next outcome? And that's a reasonable thing to ask. So my outcomes are discrete quantitative. My probabilities add to 1, and each outcome is associated directly with a probability. We also kind of mentioned that we could envision this as like having, say, a weightless bar, that's the x-axis, and having my xi's represent locations on this axis, and my probabilities represent masses at those locations. And the expected value of x, which we computed by taking each outcome times its probability and adding them together, we said that was really the center of mass. So maybe that's something like this. Maybe this is the expected value of x, because if we put a balance point here and let this system just do what it wants to do, it won't rotate right or left. It won't tilt one way or the other. It'll just stay balanced. So our center of mass of these chunks of mass here, that was our expected value. That's what it meant. And also kind of remember, let me give myself a little more space here. Also kind of remember that we really thought of this distribution, which is our like chapter 5 distribution. We thought of it kind of in relation to something like maybe law of large numbers, in relation to a sample distribution where I have classes or bins and frequencies, right? So frequency is F1, F2, F3, and so on. Now let's think about a continuous distribution. Well, let's start with just a continuous random variable. If I have a continuous random variable, something like height or weight, right, rather than maybe something like number of students in a classroom, which would be like 0, 1, 2, 3, etc. If there are 2 students in the classroom, what's the next possible number of students in a classroom? 3. You can't have 2.5 or 2.1 students in a classroom. But what if I was looking at something like height or weight? That's a continuous random variable because, somebody could be 67 inches tall. What's the next allowable height? Well, it's not like if you're 5'7", the next allowable height is 5'8". 67 inches, we could have 67.1 or 67.01 or 67.001 inches tall. If we had a more accurate measuring device, we could get more decimal places of accuracy for somebody's height. So there's no sense of here's one height, what's the next allowable height? What's the next possible outcome? What's the next possible height? That doesn't really make sense to ask. So that's not a discrete variable. It's a continuous variable. So what do we tend to do with continuous variables if we want to organize them in a frequency distribution and maybe make, say, a histogram related to them, something like that? Well, then what we do is we make classes that are groups of outcomes. So I might do like 60 to 61 inches and 61 to 62 and 62 to 63 and so on. And count the number of individuals in my sample that say fall between 60 and 61 inches. If somebody measures to be about 60.5 inches tall, okay, I mean, I rounded that. Maybe they're actually 60.51234, 51234 or something. But if they're about 60.5 inches tall, they're definitely between 60 and 61. We're not going to measure a little more accurately and then have them end up being 65 inches tall. No, we measure them to about 60.5 to 1 decimal place of accuracy. That puts them clearly in this bin. So if I make classes or bins that are a range of outcomes, say all of the height 60 to 61, and maybe I'll be a little pedantic and make these open intervals on the right and closed on the left. The way I had them originally written was closed on both sides. Then I could sort individuals into these bins, count how many individuals fell into each bin, and get a frequency distribution that feels a bit like a discrete distribution, right? Either in this bin, what's the next allowable bin? This one. What's the next allowable bin? This one. Taking this continuous variable and making it feel a bit like a discrete variable so I could make something like, say, a histogram out of it. But I chose these bins some certain way. Maybe I chose them to be 1-inch wide bins. There's nothing like, you know, there's nothing, I don't know, kind of coming directly from nature or from the data or something that gave rise to these bin widths. Why 1-inch? Why not 2 inches? Or why don't I make them all pi inches wide? Well, it's because 1 inch or 5 inches or something is convenient for me and it seems about right. But there's nothing special about that. So I could imagine, just like I said up here, I could imagine that if I'm how did I do that? If I'm considering, I didn't even know I could do that, right? If I'm considering, some continuous variable on the interval from A to B, I could say, look at classes like from A to A plus 1, A plus 1 to A plus 2, and so on. I'm not going to be worried about my square brackets versus parentheses here. I'm really thinking about a continuous variable, so it doesn't matter anyway, whether I include or not include one of these, as we'll see in just a minute here. So I could think of classes of bins that are 1 unit wide. And maybe in this first bin, I have frequency F1. And in the second bin, I have frequency F2 and so on. But maybe we could say, well, could I, if I wanted to, cut the bin width in half? Could I use bins of width 1/2 instead, going from A to A plus a half, from A plus a half to A plus 1, and on down? Could I take each of my bins and refine it, make it smaller bins, so that if I know that somebody fell into that bin, if somebody ended up in that bin, I kind of have an even better estimate of, say, what their height is, for instance. Sure, I could do that. If I cut my bin size in half, I have twice as many bins. And also up here, let's kind of imagine that we have from A to B, and I have some bin, let's say that this is A plus 2 to A plus 3, this bin that I'm looking at. And I have some folks that fall in here, some data points that fall in this bin. So I have, what is it, 3, 5, 8, 9 data points between A plus 2 and A plus 3 that fall into this bin. So F3 is 9 for this little picture here. But if I split my bin in half, if I come in here and split my bin down the middle, I notice that I've also kind of split my frequency as well, not exactly in half, but this frequency to the left plus this one to the right has to equal the original frequency. So I can split my one bin into two bins, each of half the original width, that's fine. But then my original frequency gets split into two parts as well, not necessarily equally, right? I could have had more frequency to the right of the halfway point than the left, or vice versa, or it could have ended up being split equally. So I get more bins, but each bin, more bins of smaller width, but each bin is going to have a lower frequency typically. And we can imagine continuing to do this. If I split each bin again into half as wide, I'm going to have twice as many still number of bins. And I'm going to be splitting the frequencies further. The frequencies are going to get smaller and smaller. The number of bins are going to get larger and larger. But notice that my frequencies always still sum to n, right? I have more bins, each frequency is smaller, but the two kind of like perfectly counteract, right? Because I'm just splitting my original frequency F3 into F3 superscript 1 and F3 superscript 2. These two still add to F3, right? And these were the frequencies that all added to n, our sample size. So I'm refining, I'm getting more bins of smaller width with smaller frequencies in each bin, but the sum of the frequencies is still n. So we maintain the sum of the frequencies is n, or scaled out would be 1. The sum of the relative frequencies would be 1. We maintain that no matter how many times we do this refinement and keep cutting our bins smaller and smaller. The bin width goes to 0. The individual frequencies go to 0, but the sum of the frequencies stay constant at 1. Why is that? Well, because as bin width goes to 0, the number of bins goes to infinity. Now, unfortunately, as soon as we start throwing around infinities, like we're doing here, things get a lot more complicated. So if you have some exposure to calculus, what we're talking about here will seem, uh, you know, a very old hat, I suppose. You'll say, yeah, I've seen this idea a whole bunch of times. If you haven't had exposure to calculus, this is probably a brand new idea. We're not really, we're not going to formalize this very far. But I want to explain what's happening here so that we have some intuition for some of the seemingly strange things that we're going to talk about coming up here. Okay, so in continuous distributions, how do we represent a continuous distribution? A discrete distribution we represent more or less as just a table of outcomes with their associated probabilities. But in a continuous distribution, we imagine doing this kind of splitting each bin in half, doubling the number of bins, decreasing each bin's frequency, and doing that over and over and over infinitely many times so that my bins end up with essentially zero. My frequencies all end up essentially at zero, and my number of bins ends up essentially going to infinity, something like that. So how do I represent continuous distributions? Well, continuous distributions are represented by graphs of probability density. These graphs of probability density, or these functions that those graphs represent, are called probability density functions, or PDFs, as opposed to probability mass functions. Really, that's the name for these. This is really a probability mass function, PMF, because it's telling us something about masses. Where am I putting masses along the line, or weights along the line here? When I start splitting up these boxes over and over and over and over again, infinitely many times, I'm not really talking about masses anymore. I'm really talking about density. Kind of like if I had a block of steel or something like that, I can say steel is this density. It weighs this many grams per cubic centimeter. That's a density. But a density by itself doesn't really say anything about mass, right? If I just say steel is whatever, 20 grams per cubic centimeter, well, that doesn't tell me if I pick up a block of steel how heavy it is. I have to accumulate density, in this case, volumetric density over volume, and then I can say this block of steel weighs 1 pound. So if I have a picture, say from A to B, like this, if this is my PDF, my probability density function, this graph is representing density. So at this point, what is the density of probability? Right? I could have a block of steel, or I could have a block of kind of some alloyed material, maybe like Damascus steel, where there's different types of metal that are interwoven together. And maybe at different points in that block, we have different densities. At some points, it's higher density. At some points, it's lower density. So it depends not only how much volume I accumulate, but where I choose to accumulate that volume. If I take a little chunk off of the block on the top right, that might weigh a different amount as the same size chunk of steel taken off the block from the bottom left, because maybe there are different densities in those two areas. Maybe the top right is an area with more heavier steel, and the bottom left is some lighter steel. So that's what this graph tells us. It tells us the linear density. So this is a linear 1D idea here. It's the linear density of probability. We're a little more used to from science class talking about volumetric densities. So like grams per cubic centimeter, something like that. But a linear density is kind of a similar idea. If I have a metal rod that's the same kind of metal and the same thickness everywhere, I can say something like, well, if I cut off 1 foot of this rod, it weighs 2 pounds, and 2 feet of it weighs 4 pounds, and 3 feet weighs 6 pounds, right? So I could talk about this rod weighing so many pounds per foot, like 2 pounds per foot. That would be its linear density. So the PDF represents linear density of probability. It doesn't represent probability itself. So what does represent probability? Probability is the thing that we're interested in, right? It's the thing that, um, well, the thing that we're studying itself, but it's also the thing that is necessary for inputting into things like expected value or variance or any of that, any of those kind of secondary things that we're interested in as well. So what represents probability then? Probability is corresponding to areas under the PDF. Let me, a little more room here. So if I were to look at this area, say between C and D, the probability that my random variable, say maybe a person's height, is between C and D, well, that would be this area, this red area that I've shaded there. It's the area beneath the curve in between, say, x equals C and x equals D, and of course above the y-axis, or above the x-axis. So my PDF represents linear density, and I turn a density into a mass by accumulating that density over something spatial, right? If I have steel that's like so many grams per cubic centimeter, I turn that into a mass of so many grams by figuring out how many cc's, how many cubic centimeters of steel I have, and accumulating so many grams per cubic centimeter over, say, 3 cubic centimeters. And that tells me how many grams of steel I have. It tells me how much mass I have. Or if I had a linear density like that metal bar, I can say it's 1 pound per foot. Well, I have to accumulate that over a certain linear distance. Maybe I cut off a half a foot of the bar, and then I can say that weighs a half of a pound. So I get mass from density by accumulating density over space, or in this case, it's a linear density. I accumulate probability density over distance. So I kind of add up all of the probability density that's between C and D, and that's this area. Right. So like I said here, the accumulation of mass density gives mass. The accumulation of probability density gives probability. This leads to some counterintuitive statements. For a continuous random variable, the probability that x equals any specific number is 0. So if I say x represents the height of a random Pittsburgher, we take this to be a continuous random variable, then probability x equals 6 feet 0 inches exactly is 0. Right? The probability somebody's exactly 6 feet tall is 0. Why is that? Well, if this is my PDF for heights of Pittsburghers, and here's 6 feet 0 inches, what is the area, kind of similar to this red area up here, what is the area covered by the single vertical line? Area is something like base width times height, but my base width, instead of here being like from C to D, being like D minus C, that can generate an actual area, a non-zero area. But here I just have a single vertical line, right? It's like if I said I have a chunk of steel that is 30 grams per cubic centimeter, but I have 0 cubic centimeters of that steel. How much mass do I have? Well, none, right? I have a linear density, but I accumulate it over 0 linear distance. I don't have any probability. That probability is 0. However, if I were to ask a question like, what's the probability that a random Pittsburgher is between 5 foot 11 inches and 6 foot 1 inch tall, now I am accumulating probability density over some linear distance. Now I do have an area. This is going to be positive, right? We know that there are lots of people who are between 5'11 and 6'1. So the person who's about 6 feet tall falls into this bin, they get counted, but they're not going to be exactly 6 feet tall. Another way of thinking about this is for a person to be exactly 6 feet tall, that means if I rounded their height to the nearest inch, they have to be 6'0". If I rounded the nearest tenth of an inch, that tenth of an inch digit would have to be 0 as well. The hundredth of an inch, that would have to be 0 as well. Thousandth of an inch would have to be 0 as well. Basically, when I keep cutting this bin size down more and more and more and more, each time I cut the bin size, I kind of like, roughly speaking, divide my frequency in half between the two bins, the two new bins. How can I keep cutting a number in half forever and have it not go to 0? Or if I take 3 and divide by 2, and then divide by 2, and then divide by 2, it just keeps getting closer and closer to 0. So meaningful events, or perhaps a better way to say this would be interesting events in the continuous world, are intervals. It's okay to ask a question like this. What's the probability that continuous random variable x equals some number? That's not a nonsense question to answer to ask, but the answer is just boring. It's always 0. So the interesting events are intervals, or the meaningful events, or the ones that we want to study, are intervals. So these can look like, what's the probability that my continuous random variables between two numbers? Well, now I'm accumulating probability density over a distance, over a linear distance from A to B. Now I'm likely to get some positive probability and something that's interesting to talk about. Or I could ask, like, what's the probability that X is bigger than A? What's the probability that a person is more than 5'4" tall? That would just be like accumulating, a probability that, or accumulating probability density, just kind of continuing to go off to the right as far as the distribution goes. Or what's the probability that X is less than B? What's the probability that somebody's weight is less than 120 pounds? That's starting at B and going off to the left. I'm accumulating probability density over a linear distance, just going off to the left as far as the distribution goes. Okay, so then we might ask the question, all right, well, if a PDF is represented by a function f of x, so this like curvy function I've been drawing here, this is just kind of my f of x example, my PDF. It's some function. But f of x is not a probability. Then what is f of x? What does f of xi mean? I mean, one way to answer this is, well, it's a probability density. And all of the stuff that I just said about probability densities, that's what f of x means. But mathematically, what does it mean? What it means is that for some small positive number, if I look at my f of x, this one between, say, a and b, and I'm interested in some, well, let me not call it a to b. Let me say like alpha to beta. I don't want to steal the letter that I already used over here. So we have some a here. This point is a comma f of a. Now, again, f of a is not a probability. It's a probability density. But what does that kind of mean? It means if I go some small distance out to the left and some small distance out to the right, let me zoom in on this. Come over here. Um, So I have my f function. I have my axis. Here is A. And I come out some small distance to the left, small distance to the right. I'm zoomed in, so these are small distances, but they look bigger. And if I follow these up to f itself, and I consider this area, say, well, when I zoom in like this, if I have a nicely behaved function, when I zoom in, I can actually kind of just pretend that instead of this function being curvy like it is, I can just kind of pretend that it's approximately flat. And then I can take this as the area. As long as I stay really close to the point of interest, I can kind of assume that my function is just roughly constant there. This is another calculus idea that we use all the time. And I can calculate this area. Remember, this point had height, f of a, and I have some small positive number epsilon. I'm going half of epsilon to the left and half of epsilon to the right. So this is a minus epsilon over 2, and this is a plus epsilon over 2. For whatever reason in math, we tend to call small positive numbers epsilon or perhaps delta. But that gives me a total interval width of epsilon. This red area is approximately, this area is approximately a probability. It's approximately the probability that my random variable is between this number and that number. So what do I know about this probability? The probability that x is between a minus a tiny bit and a plus a tiny bit. Well, that should be the area of this box. But wait, this box has area. It's just a rectangle, so it's base width times height. The base width is epsilon times height f of a. So if I go from a point of interest to the left a tiny bit and to the right a tiny bit and accumulate probability over that small interval, that's going to be approximately the width of that interval times f of a. So what does f of a mean? F of a is approximately the accumulation of probability over a small interval surrounding a divided by the width of that interval. That's kind of the average probability per unit distance on some small interval surrounding a. It's like an empirical estimate for density, right? If I had a big steel block, I might cut off a little chunk that's like 1 cubic centimeter, weigh and get its mass, and then that gives me so many grams, and I weighed 1 cubic centimeter, so I can estimate that number of grams per cubic centimeter is maybe the mass of the whole block. And that's what I'm doing here. So that's kind of what f of a is in a more mathematical sense. In a more, practical or tangible sense, it's all of the stuff that we talked about up here with accumulating density to get area and accumulating probability density to get probability. So f just represents the probability density, but more mathematically, it means something like this. Or in other words, if I wanted to ask something like what's the probability somebody's 6 feet tall? I go a little bit to the left of 6 feet and a little bit to the right of 6 feet, maybe 1 inch to either side, and ask that probability. I'll get an answer there, and that'll give me, the probability that somebody's within 1 inch of being 6 feet tall. Or if I wanted a little more accuracy, I could go a half inch either direction or 0.1 inches in either direction. I could pick smaller and smaller intervals to get something like more and more accurate estimates of what I might mean by something like this, what I might mean to ask here. Right? If I'm worried about, somebody being 6 feet tall, you know, they will fit my whatever, clothes that I'm making or something, and I want to know what proportion of the population will approximately fit this shirt or this pants size that I'm making. Then maybe instead of asking this question, maybe I ask something more like this. Okay, so what are the requirements for a function to be a PDF? Not every function, if we just pick some random function like sine of x, not every function is allowed to be a PDF. We have some constraints. The first is that f of x has to be bigger than or equal to 0 for all x. We see that f is kind of like a probability divided by some positive number. So more or less, f kind of corresponds in some sense to probability. But probability has to be non-negative, right? If I allowed my function to say dip below 0, I could find an interval that if I accumulate a negative density over that interval, that's going to give me a negative probability. What does it mean for some outcome to have a negative probability of happening? Right? That doesn't make sense. So my probability density has to be bigger than or equal to 0 everywhere. And also the total area has to be 1. Remember when we did this whole business of taking boxes and then splitting them up and splitting them up again and splitting them up again, if we thought of actual frequencies, here I have relative frequency, but if we were thinking of actual frequencies, because it's a little easier to think about it first, if we're thinking about actual frequencies that I have a sample of size n, if I just keep splitting up boxes, my actual individual data points, I still have the same data points. They just fall into maybe a different size box. My sum is n of all my data points. My sum is n after I split the boxes up in half as well. Or my relative frequencies are going to sum to 1, and my relative frequencies are going to sum to 1 here as well. If I just take all of these and divide by n and add them together, then I get n over n is 1, which is the same thing I would get up here. So even after the business of dividing infinitely many times and getting down to a probability density function, the total area has to be 1. So if I'm claiming that, for instance, this is a PDF on A to B, then if I investigate this probability, what's the probability that x is between A and B? That had better be 1 or 100%, right? The sum of the probabilities has to be 1. The accumulation of probability density across the entire linear distance that we're allowing has to also be 1. Now, something to note here is that some distributions, some continuous distributions, are finite like this. I'm not going to get into into a ton of detail here, but we can very easily see how this area can be 1, and that could be a sensible thing, right? We just shift the overall height of this curve up or down to make this area turn out to be 1. However, some distributions are infinite. They kind of go off forever in both directions. Like the bell curve, the normal distribution, which we'll be studying in this chapter, it goes off forever in both directions. Or maybe like the exponential distribution, it goes off forever to the right. And you might ask, well, how could it be that, right, I start chunking this up, I have a bit of positive area, a bit more positive area, a bit more positive area. I'm adding bits of positive area to other bits of positive area forever. Doesn't it have to go to infinity? And the answer is not necessarily. Sometimes when you do that, it does, but sometimes it doesn't. And I'll give an illustration here. This isn't a proof that relates in any way to normal distribution or exponential distribution or anything. It's just illustrating the concept. So imagine you have one whole pizza. So I have one whole pizza. And I want to make sure that I have a whole bunch of people to feed. So I want to make sure everybody gets some pizza. So I say, okay, you can line up. And when you come up, you can only take half of what's left. If you keep taking half of what's left, then there's always going to be a bit left for the next person, right? So the first person, they get lucky, they get half of a pizza and they leave half there. The next person comes up and they take half of what's left. They take a quarter pizza and they leave a quarter. The next person takes half of that, an eighth of a pizza, and they leave an eighth. The next person takes half of an eighth or 1/16th, and they leave 1/16th. Right? So each time we can see that this is what's taken so far, and there's 1/16th left, and we could do all the fractions and see that this equals 1. Or I could split this plus 1/16th at the end here into 1/32 that the next person gets and 1/32 that's left. I can keep doing this, split that 1/32 into 1/64th plus 1/64th, split that 1/64th again and again and again. In fact, I could keep doing this forever. I can continue to add up positive things. These are all bigger than 0 forever. And pretty clearly, that's got to equal 1. So if the things I'm adding up get small enough fast enough, then I can add up infinitely many of them, provided they get small enough fast enough. If they don't get small, if I'm just adding like 1 to itself infinitely many times, that blows up, that goes to infinity. Or if I'm adding things to themselves that get small, but get small kind of slow, like 1 plus a half plus a third plus a fourth plus a fifth, that gets small kind of slow. That doesn't quite get small fast enough to add up. That goes to infinity as well. But something like this, e to the minus x squared, gets small very, very fast, or even something like e to the minus x gets small quite fast. These definitely fall in the regime of getting small enough fast enough that we can like add up infinitely many positive things and have it turn out to be finite, or in this case, turn out to be total area of 1. So just to give you an idea that this can happen, you can add up infinitely many positive things and get a finite number in certain scenarios. And the scenarios we'll look at, things like the normal distribution or perhaps the exponential distribution, that does happen for these, that these tails get small enough, fast enough, that even though it spans the whole real line, we can kind of add up all of the area. Okay, so let's take a step back from the theorizing and let's look at an example. Our first continuous distribution. Remember in chapter 5, we had these kind of canonical distributions like the binomial distribution or the Poisson distribution. And the idea was, well, if I have a situation that fits maybe a certain set of assumptions or that I think this distribution will be a good model for, if I understand how this particular distribution works, like the binomial distribution family, and I see that I can apply it as a fitting model to this situation, then right away I know a lot. I know maybe how to find probabilities. I know what the mean is. I know what the standard deviation is just from some formulas. And that's what we do a lot of times in continuous distributions as well, even maybe more so in continuous distributions, because you can imagine that finding areas under curves like this is not the easiest thing in the world to do. So we have some distributions that either that are very important or for which calculating these areas isn't so difficult. So the uniform distribution. This is both an important model and one where computing areas is not difficult. So this is kind of the best of all worlds, but only applies to a pretty small subset of situations. So what's the uniform distribution? It is the distribution whose PDF is constant height on some finite interval. So on A to B, the PDF is constant height, and it's 0 outside of A to B. This 0 otherwise is a little bit of pedantry. We want F to be defined on the whole real line for, kind of some other reasons. So, but basically we can just think of the distribution as being constant on A to B. And if we wanted to get particular, we could say it's defined 0 everywhere else. So it'll contribute 0 probability anywhere outside of A to B. And we're saying that it has height C. I see that it has base width B minus A. And I see that the total area under the PDF is actually a rectangle. It's a rectangle with height dimension just C and width B minus A. So its total area is going to be C times B minus A. But remember, we want to enforce that the total area must be 1. That was one of our criteria to be a PDF. The total area has to be 1. So on one hand, the total area is C times B minus A. On the other hand, we want to enforce that to be 1 so that it's a valid PDF, which tells me that the height has to be 1 over B minus A. And so now we can write down our uniform probability density function, PDF. F of x equals 1 over B minus A for x in A to B and 0 otherwise. So let's look at an example. Suppose that we know that a certain train, certain like subway train, arrives every 15 minutes, but we don't know when it last arrived at the station. We don't know what the schedule is. We just know that it comes every 15 minutes. We're going to choose to model the amount of time we have to wait for the train to arrive from when we arrive at the platform as a uniform random variable on the interval 0 to 15, right? We might have walked up to the platform just as the train left and we just barely missed it, and we have to wait a full 15 minutes for it to come around again. Or we might have walked up just as it's about to pull up and we have to wait 0 time, or maybe somewhere in the middle. Since I really have no idea when it last left or is going to arrive next, I choose to model all of these times as equally likely. So I choose a uniform random variable on 0 to 15. My PDF then is going to be height 1/15th and just a horizontal line at that height. This gives me a total area of 15 minus 0, or 15 times 1/15th, total area of 1, that makes it a PDF. So let's compute the following probabilities. Probability x less than 15. Well, of course, x being less than 15, I'm accumulating probability over the linear distance to the left of 15. It accumulates all of this probability That's just one. If the train arrives every 15 minutes, I never have to wait more than 15 minutes for it. Now keep in mind, right, we're in the probability section, we're in a mathematical model here. George Box, all models are wrong, some models are useful. So you might say, well, what about the situation where the train breaks down or something? And it's, well, yeah, that would be a scenario that's not covered by this model. But we're choosing to model the arrival time of the train as uniform. So under the model, it's a certainty that the train will arrive in less than 15 minutes. Now we might ask, what's the probability x is less than or equal to 15? It's also 1. Why is that? Well, it's because x less than or equal to 15 is x less than 15, or x equals 15. But the probability x equals 15 is 0. This is a pretty important note. In discrete probability distributions, we're very, very concerned about strict versus non-strict inequalities. If I say, what's the probability I roll a die and it's a number less than 5 versus less than or equal to 5, those are very different answers. Less than 5 means 1, 2, 3, or 4. If it's a fair die, that's 4, 6, or 2/3. Less than or equal to 5 is 1, 2, 3, 4, 5. 5/6, or what, 87 or something percent. 83 or something percent. So very different answers. In the continuous world, less thans versus less than or equal to's don't really matter, because the probability that we're exactly equal to some number is 0. So if I include the equal sign or don't include the equal sign, it's the same answer. Any probability question is only changed by adding or subtracting 0, so it doesn't change at all. Or, oops, I have my answers in here. Spoiler alert. What's the probability that x is between 3 and 5? So let me come over here and actually, can I just select these and delete? Good. Come over here and erase this. So what's the probability x is between 3 and 5? Well, here's 3. Here's 5. I'm looking for this area. This area is a rectangle. Has base width 5 minus 3 is 2, and height 1/15. So it's a rectangle with base width 2 and height 1/15. 2/15 probability that x is between 3 and 5. One interesting characteristic of uniform distribution, or maybe even defining characteristic of it, what's the probability x is between 5 and 7? Or 7 and 9? Or 11 and 13? These are all rectangles of a given height with base width 2. They're all the same probability. The probability of an event under a uniform distribution only depends on the interval width of that event. 3 to 5 is 2 units. That's a 2-minute span of time. That comes up with probability 2/15. Any other two-minute span of time between 0 and 15-minute wait, so 0 to 2 or 13 to 15 or anything in between those, if it's a 2-minute span of time, it's going to have the exact same probability of occurrence of 2/15. Okay, so when we come back, we will talk a little more about the uniform distribution, and then move on to the normal distribution, where we're going to spend most of the rest of our time in chapter 6. And we'll actually see the normal distribution in almost every problem in some facet or another, really for the rest of the course. Okay, so that finishes up our discussion today. Let me stop the recording.